Welcome everyone to the fourth session this semester. And today we have two very interesting talks again, and they will be presented in a short time. But before, I want to point out that you can ask questions. So at the end of every talk, we have a little discussion round. And to ask your questions, you can use this little application from Zoom, which is called Q&A. It's on the bottom right next to the chat. And you can also put in your questions anonymously in there, so we can have a nice discussion round after every talk. And then I would say we already start with the first talk, and I would give the word to Daniel.
Thanks, Andrea. Welcome everyone, and exactly, welcome to our fourth edition of the season. Today we have the pleasure to welcome Majdeep Basu from the University of Edinburgh. He has been conducting together with Eurotube his master thesis on a cooling concept of a linear induction motor for our test facility in Vallis, which we call AlphaTube. This is the talk we will be having today. As a small short background, Majdeep has been already involved in Hyperloop since 2021. Firstly, as a software engineer at the team of the University of Edinburgh at Hype, where he debugged and programmed the coding of the sensors for the vehicle. And then he also got involved into the design of the suspension system for the vehicle, which got to be presented in the ESW 2022. Since already 1 year almost, he's the head of technology at Hyperloop, and now recently he managed to finish his brilliant career together with Eurotube on the topic on the thermodynamics. So with this said, I would like to give the floor to you, Majdeep. Thank you very much for joining, and we're really looking forward to your talk.
Thank you for the introduction, Daniel. Great, so thank you everyone for coming to this talk. I'll just be taking you through the design and development of a cooling concept I came up with as part of my master's thesis, which I did in collaboration with Eurotube. So to go through the slides themselves, just what you'll be seeing today, I'll go through the background of the project, defining the problem, the design of my cooling system, some simulations I ran, and some of the conclusions I could draw from this. Okay, so I'm sure many of you here already know what a Hyperloop is, but just in case there's any newcomers who aren't sure, it's essentially a high-speed emissionless transport method using electromagnetic propulsion and levitation, and it's propelled through a vacuum tube, and it can therefore reach speeds close to a plane due to the low pressure and low drag environments. The reason it's very good to research this is because we're currently pushing for fewer emissions, and it's good to reduce these in transport, which contributes to 37% of carbon emissions. And also society's moving faster, so transport is going to need to keep up as the world comes closer and becomes more interlinked. So high-speed methods are also in big demand. Right, so now I can go more into the actual specifics of the problem themselves. I'll start off by defining what a linear induction motor is, as this is the propulsion system used by Eurotube. It's essentially an electromagnet that consists of a primary and a secondary. In Eurotube's case, the primary, which is what creates the magnetic forces attached to the track, and the secondary is attached to the pod itself. And therefore you can push the pod forward with the relative motion between the primary and secondary. The primary consists of copper and an iron part, and this is important for later, as this is where our heat sources come from. So there are two main heat sources in the LIM, the copper coils, which heat up via Joule heating, which is essentially, as current flows, the electrons bump into atoms within the copper, which in turn vibrate more, generating heat energy. There's also hysteresis losses in the iron core, which is essentially an iron molecule resisting the magnetic force. These are the two main heat sources which I was focused on for my project. I calculated some values, and I found that the copper does heat up more, as in has a higher temperature, even though it's got lower losses due to its much lower thermal masses. And the reason we'd need to focus on mitigating the rise in temperature is because eventually the components will fail if they're allowed to increase in temperature indefinitely. And the LIM also operates more efficiently during in lower temperature environments. So some of the constraints of the cooling system were mainly geometric, in that a certain air gap must be maintained between the primary and secondary, and therefore I couldn't build any cooling system around that area, as well as the minimum temperature of the heatsink. Now, because I'm working on AlphaTube, which is based in Switzerland, I chose the average summer daytime temperature, and this should ensure that the heatsink temperature is as cool as possible in all other scenarios, such as during the night or in the winter, which means if I can design for a system which is hot in ambient temperatures of 25 degrees C, it can definitely work in cooler temperatures in the winter. So now I can go on to the design of the cooling system itself. The cooling system can be separated into 4 main parts. These are the heat sources, which is the LIM itself. The 2 heat sources I mentioned were being Joule and hysteresis. The heat absorption, which is what I primarily focused on, which is how I get the heat from the heat sources to a working fluid. A heat transport system, which is how I get the working fluid out of the vacuum, as there is no passive convective cooling inside there. And finally, a heat disposal system, which would be your heat sink. I chose this to just be a fin-based heat exchanger on the outside. However, further research can be done into, say, thermal storage, thermal energy storage, or even a district heating system. However, that wasn't the focus of mine. My focus was on the heat absorption. So one of the first things I wanted to look into was whether or not I'd have any conduction between the iron and copper heat sources, and if I could therefore only use one cooling system to cool down both. And I found that you couldn't. I did a 1D conduction analysis to derive a formula to find the temperature difference between the iron and copper. And I found that barely any heat transfers from the iron to the copper due to the insulation material to electrically insulate the copper. So I decided to come up with 2 cooling systems, which I'll go into now. First off was a very standard water jacket cooling system where I take a block of aluminium, drill some channels into it, and have water flowing through that. And I attach this to the back of the iron core of the LIM. Because the iron core didn't heat up very much, I had a fairly low flow rate, however, still maintain almost turbulence, and was able to get an average convection coefficient, theoretically calculated, of 21.3 watts per meter squared Kelvin. The heat transfer is as so from the iron to the aluminium, and then convected away with my water region. The more interesting is the copper winding cooling. As the copper is shielded inside a layer of insulation, I had to come up with something that could get fluid as close to the copper as possible without actually shielding it. Based on how Eurotube's windings are done, they are essentially copper wires encapsulated in a layer of epoxy, and then that encapsulated in a layer of insulation. I decided to have channels, copper cooling channels, inside the epoxy as well for my design. So essentially that would get me as close to the copper coils as possible, and I could have heat conducting from the copper to the epoxy and then into my cooling channels. I think this application can be used in many industries, not just Hyperloop, but it's especially prominent in the Hyperloop due to the vacuum environment and there being no ambient cooling, which is present in most other high-power machines. I could get an average convection coefficient, again calculated by hand, of 71.6 watt per meter squared Kelvin. Okay, now I can talk a bit about my simulations that I ran just to ensure that the results would work, ensure that my method would work. I used water regions and solid regions, as you can see in these images. And for my meshing strategy, I was mostly focused on the boundary of the 2 flows, because this is where most of the heat transfer occurs. I did this by using a prism layer to get a very fine mesh at those boundaries, whilst having a fairly coarse mesh towards the center. These were the simulation results. As you can see, this is for the water jacket, and as you can see, the maximum temperature I reach in a steady state scenario, this is with a constant energy source from the bottom of the water jacket, would be 310 kelvins. This was pretty good, as my failure temperature was far above this at about 390 kelvins, so I was very happy with this. In the copper, it was slightly higher due to the much lower thermal mass. I used a much more simplified geometry for this, just to save simulation time due to the university time constraints for this. The maximum temperature I reached of the solid region was about 316 Kelvin, and of the fluid region, it was about 300 Kelvin due to the heat being channeled away at a very fast rate. Those were my simulation results. I'll now just tell you about my conclusions that I could draw. So I can very much keep the water jacket and the copper coils far below their critical temperature of 390. However, I think I could have done a bit of further optimization if I had more time to ensure that I could keep the system as cool as possible, as close to that ambient temperature of 25 degrees C. You can do this with geometrical optimizations and also changing the material of your epoxy and your insulation. I assumed a worst case material for both, having very low heat transfer coefficients in those. You can also do a bit more analysis on the refrigerants that you use. I used water. However, you could look into a better material for this. Okay, since the alpha tube isn't manufactured, I'd say the next steps would be manufacture that and then implement this cooling system on that so that it can actually be tested and not just simulated. That's it from me. Thank you all for listening. If there are any questions, I'm happy to get them out now.
Thanks a lot, Megdeep, for the interesting talk. I see also there are questions from the audience, so we can just jump straight into them. There is someone asking about the methodology you implemented. Did you consider the manufacturing type to be as simple as possible for future adoption in large-scale Hyperloop systems? So meaning how scalable would be then the system? Have you taken this into consideration?
It's not something I considered a huge amount when designing. However, I figured out a method I would use to manufacture the copper winding system towards the end, in which how we do it at the moment is the copper is placed into the slot and then epoxy is poured in for just copper coils. What I would do is place the tubing themselves into the slot and the copper coils and then pour the epoxy in. However, I haven't thought about large-scale manufacturing.
Okay, and is this type of concept we also see from industry already, or would it be a complete new development, this encapsulation?
I'm not sure, but I believe it is already in industry, encapsulating copper coils in epoxy. I don't see why I couldn't do the same with copper tubes as well.
Thanks. We have another question from the audience. Someone is asking how much of a problem is the isolation of the cooling of the motors? Are there any considerations you could share? Basically, more generally speaking now.
Could you repeat the question? Sorry.
The question would be how much of a problem is the isolation of the cooling of the motors? I think in an order of magnitude, someone is asking how much impact does this cooling have in the overall system, let's say, when accelerating a Hyperloop vehicle.
Right, I see. Okay. So the main considerations I took into, I guess, overall impact was the energy used to pump my fluid. I had fairly relatively low flow rates that were kind of middling actually when I was designing this system. So the energy used to pump the fluid wasn't a huge amount, to be honest. As I said, further optimizations can be done to reduce your flow rates as well, so that you could get the same amount of cooling from that. The other main consideration I would take into account would be the potential of shorting because of how close fluid is to the current carrying coils themselves. However, I believe having that epoxy layer essentially isolates the coils electrically from the actual fluid.
Mm-hmm. Okay, because this is then linked to the next question in terms of sealing against the vacuum environment. Have you looked into ensuring that these cooling channels could stand a vacuum and thus a leakage could be prevented?
Mm-hmm. I haven't actually looked a huge amount into preventing leaks due to the conceptual side. However, my main suggestion would be to use, again, epoxy at every point possible. If a leak does occur, there would have to be, I guess, stoppage for maintenance, is all I could really see being the solution. However, yeah, it's something to be mitigated.
Because these segments, how long would it be along all the launcher?
So I did a segment of about 1 meter for all my analysis. That's what I assumed it would be, just a 1 meter of linear induction motor. Yeah.
Mm-hmm. Excellent, thanks. Then there is the next question. Someone is asking if the electrical isolation of the coated coils would need an epoxy layer. The reply is yes. Have you looked at something that would be in direct contact with the coils when talking about electrical isolation?
So when I was doing my research, I found there are some oils that could be used for this as well. You could even go as far as drilling channels into the coils themselves and having oil flow in there. However, I thought this might be even more difficult to manufacture than the system I came up with making such coils, which is why I kind of moved away from that side.
Understand. And now when looking at the simulation of the holes itself, someone is asking if you also looked into increasing the diameter of the hole, meaning decreasing the wall thickness between the holes to increase convection.
Yes, I did do that. However, obviously making it as thin as possible helps you the most. The main dimension I was concerned about, though, was the side dimension. If you can see, I'm very close to the edge of the coil itself. So that's kind of what constrained me, and I made it as big as possible as I could with that side dimension whilst maintaining a circular shape. However, you could do a bit more optimization, maybe have an ovular shape as well, so that you could decrease that distance between channels.
Okay, very, very nice. And let's say as an outlook for next studies, what would be then let's say the work package on the topic you would be further looking into it if you would need to do so?
So my next step would be optimization of the system, seeing what I could change about the working fluid, some of the materials used in here as well, and improving this simulation model I made to account for more of the epoxy within the actual coil geometry. And if I had more time, that it would take a while to simulate. But again, if you have more time than me, you can definitely go ahead and do it. That's what I would say looking into.
Excellent. And then to conclude, someone is then asking if the thesis is openly accessible.
Unfortunately, it's not. I believe the uni currently have rights on that, so I don't think it is at the moment. I can work on making it public, though.
Okay, probably also an idea and an option is to get in contact directly to you in case there are further questions into the topic.
Absolutely.
Excellent. Thank you very much, Megdeep, for the interesting talk. Then I would leave the floor to you, Lucas.
Thank you very much. And I have the pleasure to announce our next speaker. Federico, thank you for being here. I'm not even trying to announce your your last name. Maybe you could do that as well. You're the dynamics unit lead at Zeleros Hyperloop, and you just finished your PhD. So congratulations to that. I've seen on LinkedIn that you have done simulations of, was that 100 million different designs? I didn't know how to interpret that. Maybe you can tell us about that in your presentations. Very much looking forward to that. And with all that said, the floor is yours.
Perfect. Thanks for the introduction, Lucas. So this is the presentation I've prepared. So I'm Federico Juesma. I'm propulsion engineer at Zeleros, and also I recently finished, as Lucas said, my PhD about, well, Hyperloop research. So this is the presentation, part of the presentation I prepared for the defense, and essentially this description of design and optimization of Hyperloop capsule and the model used for it. So without further ado, I'm gonna start. Here we can see the index, present an introduction of what is Hyperloop considered as we see it, because there are different definitions of Hyperloop. Then I move on description of the aerodynamics of the capsule, which is a very tricky point on this concept. Then the simulator itself, and finally the conclusions. So about Hyperloop, what is Hyperloop? I'm sure we all know what is Hyperloop, but at some point there are always some differences of what we conceive of Hyperloop in different approaches. Here at Zeleros, well, we think Hyperloop is a ground transportation system that can travel up to 1,000 kilometers per hour with fully electric propulsion and zero direct emissions, and connecting hubs up to 1,500 kilometers away. And also, as the system is enclosed on a tube, as you know, we have very strong resistance to different conditions, such as snow, wind, rain, whatever. So I also did a research about the different approaches that lead us nowadays to try to develop a new system, a new ground transportation system. So I started with the steam locomotive, developed it at the beginning of the 19th century. Then we developed at the end of the 19th century the electric train. And nowadays the next evolution is what we consider as the maglev trains, operating in China commercially since 2002 and before in Germany. This is the Transrapid, and the other maglev trains, most important maglev train nowadays is the Chuo Shinkansen, which is using superconductive magnets in Japan. In parallel, also there are another approaches slightly different to the trains as we see it all the days, which is the atmospheric railway developed at the mid-19th century. This one can be closer to Hyperloop because we have a vacuum propulsion, let's say. In this case, I will use this pointer to make it easier for you to understand. The train used a tube in which vacuum was created to propel the capsule. Not all the train is in vacuum, but only a piston below the vehicle. And this is what propelled the train, this atmospheric railway, on the 19th century. Nowadays, we still have this operating. A company called Aeromobile is operating it commercially in Indonesia and in Brazil, and is expected to open another line in a few years. And another approach, even closer to Hyperloop, is the pneumatic railway. We have a first operation even with passengers, in which a small capsule was placed within a tube, and the vacuum or the low pressure environment was created on the whole tube, not only on the piston, as we said, as we saw before. And well, this operated only 500 meters. It was not a big commercial operation, as you can imagine, but well, this is kind of close to what we see Hyperloop. And this is important because the combination between the maglev and the pneumatic railway is what we kind of call Hyperloop. It's kind of a fusion of both concepts. And here is the Hyperloop description of the Zeleros capsule. Well, obviously we have the infrastructure with the tubes, in which the low pressure environment is created thanks to the vacuum system. And there's also a linear motor, in which part of the motor is on the track and part is on the vehicle. Also the cabin. And the main difference on the Zeleros approach to other Hyperloop concept is that the main propulsion system, or the cruise propulsion system, is based on the aerodynamic compressor instead of using a full linear motor. So this aerodynamic compressor comes from the aerospace industry, the same as we see on the engines on the planes, but using electrical propulsion, obviously. In more detail of the capsule, we have the levitation system placed on top of the vehicle, hybrid electromagnetic suspension, and inside the vehicle, we have here the cabin, the energy storage system, and the most important part is the ducting for the propulsion. So you can see we have the compressor on the front of the vehicle. Then there's a conduction of the air duct that goes below the cabin, and then the nozzle, which is the exhaust of the air, and this is what provides thrust to the vehicle. Then I will explain in more detail the aerodynamic studies I developed for the capsule to understand what is happening, how the flow behaves, and which is the drag, the performance of the different components. But firstly, I have to explain a very important problem that happens to anything that wants to travel in a closed environment, especially at high speeds, such as Hyperloop in this case. If we have a vehicle traveling at a certain speed or Mach number in a closed environment, this closed environment is defined by the blockage ratio, which is the area of the pod with respect to the area of the tube. What happens is that the flow at some point reach Mach equal to 1 at the passage between the pod and the tube, and no more air can flow through through the passage. So the air blocks, and the speed cannot be increased without increasing the power exponentially. So this kind of blockage, or this kind of limit, is known as the Kantrovich limit, and there's analytic solution to this problem with a lot of simplification, which says that depending on the tube size and the speed of the capsule, we have a region in which we cannot operate, which is the choked region of the Hyperloop. So to put this on example, if we have a 3-meter pod and we want to travel at 700 kilometers per hour, the maximum or the minimum tube size is corresponding to this blockage ratio of 0.19, which corresponds to a 6.8 meter tube. So at 700 kilometers per hour, we'll need almost 7-meter tube or higher if we want to avoid this Kantrovich limit. So the idea we had was, does the compressor improve the performance of Hyperloop? So can we overcome this problem? Can we reduce the drag and the power of the capsule? And to validate this, we developed 2 different cases in CFD. One without the compressor, which is essentially a bullet, and one with the compressor, similar sizes, equivalent, and instead of having all walls, we have a compressor on the front and a nozzle on the rear. So I'll show you the results on the CFD. We've differentiated 2 different cases, one in which the tube is larger compared to the vehicle, which is this one. And this case is with the compressor, and this case without. Essentially, the flow behaves the same in both cases, but with the compressor, we can reduce the weight of the vehicle, which is kind of beneficial. It reduces the drag. But if we want to move on lower tube sizes, in another way, a higher blockage ratio, the use of the compressor is compulsory at some point, because the flow behavior you can see here is kind of supersonic, and this generates a lot of drag, a lot of problems on the induced pressure, induced temperature on the tube, instabilities, a lot of problems that can be overcome with the use of a compressor. So to put these results in an easier way, in only one plot, we compare the drag coefficient of the concept without the compressor and the concept with the compressor, which is considerably lower than the previous one. And well, this allows us to use smaller tubes and consume less power. And going back to the example, the truth is that if we want to avoid the Kantrovich limit on a pod with a 3-meter diameter, in this case, instead of using a 3-meter tube for a pod without compressor, we can add compressor and use a tube of 4-meter diameter, which is equivalent to the first one. So in this example, it's very easy to see which is the main benefit of having a compressor in a Hyperloop capsule. Once this study was completed, I move on explaining the simulator, which is the main point of my thesis. The simulator wants to provide the performance of the Hyperloop capsule, considering that we have levitation, linear motor, and a propulsion based on the aerodynamic compressor. We assume that the case is steady, we only analyze cruise phase, and that the tube is infinite, so that we don't have end effects on the tube. And also we only analyze the longitudinal dynamics for this problem. So only forces and movements on the axis of movement is taken into consideration. The forces appearing on the problem are the external thrust provided by the linear motor, the magnetic drag provided by the levitation, and the thrust and drag of the ducting and propulsion system. So if we see the model as a black box, the dynamic model, we have inputs and outputs, obviously. The inputs to the model are the thermodynamics of the problem, such as temperatures, pressures, flow speeds, performance of the compressor. The mission we want to accomplish, the technology level, for example, the weight of the batteries, the power electronics, and all the different components needed for the capsule to work, geometries, and other vehicle parameters. And the outputs are the power, the mass of the different components, the length of the different components, and the most important thing is the net thrust, which is the subtraction of the thrust and the drag of the vehicle. So if a net thrust is positive, the vehicle is able to reach a certain speed. This is the model. Obviously, I don't want to explain in detail what you are seeing on the slide, but I want to focus on the 4 different big boxes you see on the model, which is the geometry definition, the thermodynamics, the solution of the system in terms of power and energy, and the mass and length solver of the vehicle. In terms of geometry, we got inspired in existing cabins and existing vehicles, which is more similar to an airplane. Depending on the cabin size, we selected 3 different cabins for the simulator, 2+1, 2+2, and 2+3, depending on the number of seats per row. And well, this is taken from existing airplanes. So we are very confident on the dimensions we use on this Hyperloop simulator. And also the system solution is based on the power transfer diagram of the Hyperloop. In this case, we use the compressor. So what provides power to the flow or to the system in general is the compressor. The compressor is moved by a motor, then the inverter, and we take the energy from the battery. On the other part, there's a turbine that enables us to regenerate part of the energy from the flow. The turbine is connected to the generator, to the rectifier, and well, takes back energy to the battery. So this is going in real time. As we draw energy from the compressor, the turbine draws energy from the flow to recover part of the energy. Not only we have the power of the turbine and the power of the compressor, but from the battery, we take power to the auxiliary system of the vehicle and power to the levitation, which is quite important on this system. And also, as this is a general overview of an example of a Hyperloop capsule, we use several parameters to describe how much space and how much weight does the different system occupy on the vehicle. So we use parameters such as the volumetric density and mass density for the batteries, the power electronics, and the motor. And moving on to the results, once the simulator is completed, we've done an optimization study to get the optimum capsule in a certain operation point. So the operation point is shown on this slide, certain speed, a cruise distance, pressure, and temperature. So going back to the black box, this is the simulator. The goal is to optimize the net power. In other words, the energy consumed in a certain route. And we've done it for two different passenger on the vehicle or seats and two different tube sizes. And we've used several variables to optimize the system. We can see this set of variables in a more visual way. We have the Hyperloop capsule. So the degrees of freedom of the problems are the performance of the compressor, the performance of the turbine, the area of the nozzle, the cabin size, and the diameter of the whole vehicle. With this, this is, well, as Lucas mentioned before, the optimizer did 100 million simulation. Obviously, not all of them appear on this graph. There are several graphs that appear in my thesis, and even more that cannot be put on a paper. But the most important thing, obviously, is the optimum. And well, remember that the optimum variable is the net power, and we've selected the vehicle that accomplishes all the requirements we imposed on the system. So this is placed on this slide. The number of passengers, the tube diameter, the size of the vehicle. Well, I want to focus, for example, that the turbine recovery is part of the energy at 10%, and we use less power than the high-speed rail to reach 3 times more speed. The simulator also gives us the power, the mass distribution of the system. Half of the mass is going to the energy storage system, and the rest is very important, for example, for the structure and obviously the payload. We have to, well, enclose the passengers or cargo or whatever. And well, obtaining the optimum Hyperloop is very important, but how much or how does this Hyperloop compares to the other transportation system we have nowadays? In this slide, I compare with the high-speed rail, the two different maglevs traveling at high speeds nowadays, which is the Transrapid and the Shinkansen. And I also use an airplane. This is the Embraer 190 for a short-haul route, and an Airbus 321 for a long-haul route. In terms of energy, Hyperloop compares to the train and the maglev, and is far better than the airplanes. And in terms of speed, we can differentiate two different speeds. One is the maximum speed, and the other one is the average speed. The most important one is the average because it relates directly to the travel time, what the passenger, how much time has the passenger have to be on the capsule or the vehicle. And in this case, in terms of average speed, Hyperloop is very competitive to the plane. It is faster than the short-haul plane and a bit slower than the long-haul. And obviously, it's considerably faster than the train and the maglev. We can see this slide in a different way to see how Hyperloop compares to the plane, which is its direct competitor on short-haul routes. For example, in this case, that we go up to 900 kilometers, we taken real routes, and we've seen how much time does the plane take to complete this route, considering the taxi and not considering the taxi. And we see that up to 800 kilometers, Hyperloop is very, very competitive to the plane. We consider that Hyperloop also takes 5 minutes to do the vacuum before a launch. So, well, it will be like the same travel time if we use a Hyperloop or a plane on these distances, or even faster if we use lower distances. And finally, the conclusions are the approach of Zeleros is quite unique because we are the only ones proposing a Hyperloop with aerodynamic compressor as a main propulsion system. We know that this compressor enables us to overcome the counterweight limit and reduce considerably the drag or the power consumed. Well, we've developed a very deep model for Hyperloop prediction, and we can use this model for optimization, any operation point. And well, as a comparison to other means of transportation, in terms of efficiency, Hyperloop is as efficient as a train almost. And in terms of travel time, is very competitive, similar or even better than an airplane. And this is the end. Thanks for your attention.
Thank you very, very much for your great talk. I think we gained a lot of insight here, and there's really, really a lot of questions that we have gained for you here. So I'll just start them right away. First one is, did you consider the pressure drop across the duct and its friction factor, that this limits the maximum vehicle length, which is powered by the compressor? So yeah, the question about the pressure drop at the duct.
Yeah. The model considers the pressure drop on the tube and on the internal duct of the vehicle. In fact, it's not appearing on these slides to reduce the presented time, but we've developed a funnel model which is predicting the friction on this duct, our own funnel model. Yeah, because this case is quite particular. We have different wall speeds, so the friction is difficult to predict. This is not a cylinder, it's an annular domain or a general shape. So yeah, we've developed even our own friction model prediction, and we consider, and even there's a loop to consider the pressure drop due to the length internally and externally.
Okay, thanks. The next question is also very technical. Since the compressor and the turbine shaft are decoupled, how do you make sure that the shaft is turning synchronously? And with a bracket on after the question, this has a major influence on the overall efficiency of the system.
Well, as they are decoupled, they don't need to be synchronized, if I understood correctly the question. But yeah, we have a new degree of freedom compared to a general aero engine. We don't have this mechanical connection. This is an electrical connection, and we can move at different speeds, the compressor and the turbine, so they can operate at different points. So this is a very big advantage. They don't need to be synchronized. We have to ensure that the compressor does not enter into surge. But well, this is even easier here as we can move freely the compressor.
That's great to learn. I didn't even know that about the system. Great. Did you ever compare the energy consumption with other modes of transport? Well, we have just seen that in terms of development of necessary infrastructure to let the Hyperloop run. So I think this is also the energy consumption over the whole lifetime of the infrastructure, if I consider the question right.
About the energy consumption of the infrastructure, we haven't taken this into consideration for these figures, but yeah, we did a preliminary study, and well, this is not as relevant as the Hyperloop consumption itself of the capsule, and also with preliminary design, we know that with, for example, solar panels placed on the tube, we have several orders of magnitude more power than the one we need for the example for the pumps. So yeah, if we added the consumption of the infrastructure, it will increase slightly, assuming that there are no solar panels, but still compared to the consumption of the capsule is negligible. So it wouldn't affect anything.
Did you also consider a life cycle analysis? So the emissions as well as the energy needed to set up the infrastructure as well over a given lifetime?
Yeah. Well, with this study, we haven't taken this into consideration, and obviously this is a very important part of Hyperloop, and yeah, we need to do this study, obviously.
Yeah, I see that too. We also have some projects that are looking into life cycle performance, and I think that's a big factor, especially if you're dealing with concrete.
Yeah,
putting out a lot of emissions. Yeah, true. Another question: since the compressor and the turbine shaft are decoupled, how do you make sure that the shaft? Oh, I think that's the same question again. Looking at the duct under the battery pack, was it really under the battery pack or was it above? It was under, right?
So yeah, it was under, but I didn't understand the last part.
How did you deal with the losses when looking at the choked flow and the choked waves created through the compression of the flow, and the diffuser slope seems to be steep? So a few questions about aerodynamics here, especially within the capsule where you direct the flow.
Well, yeah, I mean, the thing is that here, this is a render of the system. So, for example, I want to go back, but there's a lot of slides.
That's a lot of information.
To the animation. Yeah, well, this is a render of the system. Obviously, the duct is not as thin as this one, otherwise it will be blocked. We've considered the minimum area that enables the air not to block. The same problem as I presented on the tube, the country width limit, can happen within the vehicle. So none of the cases taken from the simulator are blocked inside the vehicle. It is considered that the pressure of the compressor after the compressor is enough to maintain subsonic flow on the whole vehicle, and this is why part of the energy has to be recovered on the turbine, because we need to increase the power of the compressor to overcome the cabin due to space on within the vehicle. So and this transition will be longer compared to what we see to avoid pressure losses. So yeah, so this is a render, just a render.
Okay, it's longer and a little bit thicker to not have a choke flow. Okay. There's a lot of questions about the compressor here. Is another goal of the compressor to save energy, or are there other big advantages, or is that the only advantage that you see? Apart from making the tube smaller, as we heard.
Well, we can make the tube smaller, we can save energy in terms of stability. Well, because of the flow is not shock, well, it will be more stable, the flow. Another problem we've seen is that the increase of temperature of the flow can be well, very big problem if we don't use the compressor. As well, all the losses that has a Hyperloop without compressor are going to increase the temperature of the air, and the less air is on the tube, more temperature is gonna build up on the tube. The compressor minimizes considerably this temperature effect. Yeah, another advantage is well, compressor do operate at this speed range and mass flow range we need for Hyperloop on an airplane. While linear motors do exist at 500 kilometers per hour, 431, but are not as common as the compressor on the aerospace industry.
Okay, so it's used already. Well, with regard to the temperature that you just spoke to, the reduction in temperature that you have for the tube, there will be temperature buildup for the vehicle. So is there any interesting insights into how you manage the capsule's heat dissipation, considering the immense heat output from the compressor and through the compression of the air?
Yeah, well, that's a good question. In fact, one of the improvements after the thesis is the thermal management on the vehicle. Yeah, obviously all the systems are gonna heat, and yeah, we need to extract the heat from the critical components as soon as possible. The thing is that the air within the air duct, so after the compressor, is not hot. It's not as hot as one should expect, because we cannot maybe think about the air on a combustion chamber. After the compressor, if we intake the air at 300 Kelvin, we may have 370 Kelvin or even less. So
Okay.
it is a problem, yes, but it is not 1000 Kelvin. So it's you need considerably less power to dissipate this thermal increase. In any case, and this is a problem for any Hyperloop concept, all the temperature buildup on the vehicle, well, we need to figure out the best way to extract this temperature, or to reduce these thermal problems, because outside there's no convection. So yeah, this is a problem not for the compressor, but for anything that heats up on the vehicle.
Do you have any heat management? Do you have any heat management system already on the pod? Anything that takes heat?
Well, at this state, we've figured out several ways that can be a good solution to the system. We don't have final one, but yeah, the thing is that, for example, all the currently all the heat coming from the motor and the battery is going to the walls of the vehicle, and this goes to a heat sink placed inside the vehicle, which is a mass addition on the vehicle, but helps to complete our route. This is a possible solution. Another one will be to apply an active cycle inside the vehicle, a Rankine inverse cycle, to reduce the temperature of the flow, to have a pressurized tank in which we have a cold gas, and that helps us to exchange temperature. Well, there's different proposals, and yeah, nowadays we are researching on the temperature, on the thermal management of the system.
Oh, thank you. Then there's one more question. When looking at the other Hyperloop players and the propulsion systems, Hard, YouTube, Virgin, Hyperloop 1, and all of those, how doable do you see converging towards one propulsion system for it to be standardized?
Yeah, that's definitely a good question. And well, even if we propose the compressor and other players are proposing a different system, there's nothing written on stone. And all of us, I think, we are open to hear what the others say. And well, this is not my part, obviously, but I think that this system can combine. For example, in this case, we have still a linear motor. So we need a system to accelerate the vehicle, and probably can help at some points of the route to overcome hills or after turns. So we are using still linear motors, and the other players are using linear motors. We've seen that due to aerodynamic effects, the compressor is quite beneficial on these operation points, but still, Hyperloop is not designed. And yeah, I think at the end, or everyone will be using the same propulsion or propulsion system in program, or at least the different concepts will be able to operate on the same route.
Yeah. And we're seeing that some considerations are done with respect to, for example, linear motors to all get to one technology. But there's one question I don't really get, but maybe you have an insight into that. Are curved sections being considered for the Hyperloop? So I think that means the infrastructure itself. And is the compressor in such a case undergoing any change to maintain the same performance? I believe that's probably not needed, right?
on a core section.
Yeah.
Yeah, I think we will have problems. The compressor won't due to the intake. This will be not a major problem for the compressor. I think we are reaching the limit on the passenger comfort before the compressor even notices the system is on a core.
Yeah.
In general, in Hyperloop, one of the biggest problems is that at 700 kilometers per hour, for example, the radius of the curve has to be extremely high due to passenger comfort, not due to any technological limit. So yeah, the compressor won't notice. For example, in aerospace, the turbofan is designed to withstand a lot of cross air, and in this case, we are not having the cross air due to a curve will be negligible compared to what is designed on an airplane. So yeah, I don't see this a problem for the propulsion.
Maybe we are just finished with the seminar, so maybe we can have 2 more questions here, 2 quick ones. First of one, is your thesis openly available? Is one from the participants, and then how much thrust is created from the compressed, or maybe you can finish with that one.
I didn't get the first question.
Is your thesis openly available?
Yeah, it is open, my thesis. We've published an open version of the thesis. I don't think it is still, it is yet available, but it will be soon.
We'll keep an eye out for that.
Yeah, you just have to look for my name or the title, and it eventually appear. And how much thrust can provide the compressor? Well, it is a tricky question because we don't use thrust itself. We use thrust and drag on the same variable because this system is quite different to differentiate.
Mm-hmm.
But we still talk about kilonewtons or several more 10, 20 kilonewtons, but it's very difficult to define. So we are talking about, well, if you take the power and divide by the speed, you can have a force, for example.
Yeah.
So we are talking about a very, very large amount of thrust.
Well, thank you very much. Thank you very much for all of your insights and your willingness to answer all of these questions. There were a lot of them. And I will just hand over to Andrea to finish off the seminar for today.
Yes, thank you, Lucas. And thanks a lot to our 2 speakers today for their very interesting talks and their insights into their work. And thanks a lot to everyone joining today and for all of the questions you had. And we will continue with this edition in 2 weeks because next week is going to be a holiday. And we will have 2 very interesting talks again. The first one will be from Shady El-Shatter from Swiss Loop Tunneling. He's a mechanical design engineer there, and he will talk about the whole system and about their design challenges they faced. And the second talk will be from Quintrons Hyperloop, and from Kartik Kulkarni, who is the co-founder and COO, and from Prasanna Kadambi, who is the CTO at Quintrons Hyperloop. And they will talk about the process methodology for the development of the high-performance concrete for Hyperloop tube application. So thanks again, everyone, for joining in today. And I hope to see a lot of you in 2 weeks. And so now I wish everyone a nice evening, and thanks again for joining. Bye.